Okay, so today's speaker is Saverio Cambioni. Saverio is from Caltech right now, but physically actually still in Tucson. Saverio did thesis at LPL at University of Arizona with Professor Asper on application of machine learning to planetary sciences, and basically interested in machine learning models to analyze telescopes, spacecraft, and meteoritic data to better understand why planetary bodies are so diverse. So I think we'll hear about his related work in fantastic topic. So Saverio, actually, Kemba, would you like to, before Saverio starts talking? Yeah.
Yeah, so just to remind everyone, please keep yourselves muted. If you have any questions during the talk, you can put them in the chat and then I will read them to Saverio. Otherwise, hold your questions until the end. That's all I have to say. Saverio, the floor is yours.
Thank you very much, and thank you everybody for coming. I'm very excited to be here to present about this topic, and of course I would like to acknowledge first of all like all the people that are working on this topic that are listed here. There are other also co-authors on single papers that I will shout out during the talk. And indeed, today the topic I would like to talk about is how we can improve the realism of collisions in planet formation models, in particular focusing on the topic of how we can use machine learning to do that. And here is just to give you an idea of what I'm going to touch on. I will talk about, after a brief introduction, on the methodology of machine learning that we have been using, and the several applications that we have been doing. And then I will focus on future work. And I would like to leave some time for discussion and questions at the end. So the main question that is behind this project is a question of planetary diversity. This is actually what I'm very interested in from a research point of view. Just looking at the solar system, but also, of course, looking at exoplanetary population, we know that the planets are very diverse. And in the solar system, we can kind of see that as you go at smaller and smaller sizes, so like terrestrial planets to asteroids, you can see that the diversity of these bodies increases at the point in which then you get to the small asteroids that are very diverse. So how we get this diversity and what is the main driver of this diversity is what is the scientific rationale behind this study. And one driver of the planetary diversity is the effect of collisions. So after nebular gas dissipation, the growth of terrestrial planets from embryos to planets typically and canonically is considered to happen through similar size collisions, which are referred to as giant impacts. And here on the right, you can see a fun exercise that we did when I was at U of A. We took one simulation of this collision and we rendered it in virtual reality to give an immersive experience of this intrinsically three-dimensional event. So you can see here the projectile coming in over the target, and this, in this case, is kind of a merging collision. And this project was funded by the Graduate Professional Student Council and done with Dr. Kyle Pearson and Dr. Emsen Huber. So what you are seeing here is the results of a smoothed particle hydrodynamic simulation, which is the state of the art for simulating collisions between planets. Without going into much into the details of SPH, what I think is important to keep in mind is that there are these two planets modeled with particles. Particles have properties mooted over a group of particles using kernel functions, and the law of physics, so conservation of mass, angular momentum, shocks, and conservation of energy are assessed. This simulation, especially in terms, depending on the number of particles, can take hours, if not days, to complete. And on top of that, the outcomes of these collisions can be highly diverse depending on the impact angle, defined here as the angle between the incoming velocity of the projectile and the conjunction between the two bodies and the velocity and the masses. The outcomes can be very different. And one realization of the last 2 decades is that the most common outcome for a combination of impact angles and impact velocity is not the merging of these 2 planets that you see here, but the basically the case in which the projectile hit the target but escapes and keep running, so it's not gravitationally bound. And this is what commonly referred as an hit and run collision. Going beyond these schematics, here I have some movies to give more an idea of what I'm talking about. So these it's a projectile and a target. If the projectile comes in with a low impact velocity and low impact angle, the result is a merging, so the 2 planets merge in a bigger planet. If you increase the velocity of this collision, the collision will end up to disrupt the target and obliterate the projectile with dispersion of material, as you can see here. Then if you increase the impact angle, keeping a low impact velocity in a low in the bottom left, you can see the effect of a Grayson merge collision in which the projectile hit the target, but then tries basically to escape and comes back, and this process is basically creating a disk of material, and this is kind of like the canonical scenario for moon formation. And this is instead a hit and run collision in which the projectile managed to escape because it enters with a higher velocity. So here is just to give an idea of how different these outcomes can be as a function of the impact angle and impact velocity. Skipping ahead a bit, like this is a figure of a paper that is actually now in revision, in which we map the different outcomes in the parts of the parameter space in different outcomes of the collision. So here is a plane of impact angle and impact velocity, and it is a collision for between a planet of 0.1 Earth masses and a projectile that is 70% its mass. And here, I don't gonna go all into all the details, but if you get the largest remnant, which is what remains of the target, and the second remnant, which is what remains of the projectile, if basically managed to escape, so a hit and run collision, you can see that you can range from indeed accretion to core erosion to hit and run. So the question that arises is how you can capture this diversity and translate them into planet formation models, so that every time that the planets, embryos collide to basically create like planets, how you do this process, model this realistically. And if I should like parse the...
Saverio, before
yes.
you go on, we have a question from Eugene Chang, who asks, how well can one keep track of the phases of the post-collision material? So solids versus liquid versus vapor.
Yeah, that's a great question. So I wanted to mention that these collisions that I showed so far are fully fluid, in the sense that they're like the planets are in a fluid state. With respect of vapor, that's actually a very important point, because like I mean, you can have energies that vaporize material. So these actually the technicalities of how you account for the different phases. It's a big question for an SPH, because there is a limit to what you can do actually in terms of accuracy and what you can call vapor and or condensed phase. That's like a hard maybe to say. One thing for sure that we can say is that these type of collisions are very good to have an estimate of the mass of the remnants, and other basic quantities, such as like the orbits and the core mass fraction of the planet. And I will touch on that during the paper, but during the talk. But that's a very, thank you for your question, Eugene. That's a very important question. And if you have any follow-up question, I would be happy to talk more about this. Regarding so these two kind of like central models, it's a model that there are in planet formation for collisions. The two end members, let's say, are perfect merging and inefficient accretion. So perfect merging is the assumption that when two planets collide, they always merge in a larger planet without production of debris. This is computationally convenient because basically in an embodied code that has like planets orbiting a central star colliding to become bigger planets, you have the number of particles that decreases over time. And also it's easy to sum up like the masses of the planets and get to bigger particles. However, there are many studies that shows that this is not the case, and both from a point of view of SPH simulations, but also from a point of view of dynamics of basically how the planets grow. And also there is an argument of angular momentum, because you are not only bringing mass into the planets if you merge two planets, but you're bringing also angular momentum. So you end up with planets orbiting, spinning very, very fast. So there have been the realization that there was the need to improve the realism of how collisions are treated. And so inefficient accretion models are been developed in the past. There have been a lot of work on this, mainly based on scaling laws, so using some results of collisions, typically SPH, and scaling the results to predict a different impact condition using some scale invariance quantity. But these are based on physics assumptions. So you make a physical assumption and an assumption on the fitting of these simulations. Another approach, which is the most rigorous, but also the most computationally expensive, is to model all collisions on the fly. So every time that you have a collision, you stop your embodied code and you run a full SPH simulation. This can take forever, like has the problem that then you don't know how many particles you would track, and in the embodied code, the particle number can explode. So then, like, if you downgrade the resolution of the SPH simulation to do this process in a feasible way, and then end up with a set of embodied simulations that is large enough to do statistics, then like there are studies showing that the prediction could not converge in terms of SPH. More recently, we put forward an approach that uses instead machine learning to train surrogate models, and I will qualify what a surrogate model is in a second, on SPH simulations to then provide these functions that allow us to predict the outcomes of each collision in the embodied code in a way that mimics the SPH simulations we know with a known level of accuracy. To provide a bit more details on these, here on the left, you see a schematics of a very complex system, physics-driven, and that takes a longer time to run, to produce an outcome. So in our case, it will be the SPH simulations that I show you. And on the right, instead, you see what I define as a surrogate model, which is a case of a simple function that has a very short runtime, that doesn't know the physics, only knows the data, and is able to match from like impact properties, here represented with X, the impact outcome, because I've been shown several examples of this relationship between inputs and outputs. So the surrogate model is a surrogate version of the SPH model, and if properly trained and tested, can provide a similar a similar prediction with respect to SPH simulation, but de facto very fast, and so in a very short runtime. Here, just again, more details on this, just to open the black box, try to open the black box of machine learning and look into it. And so here is the case of then a training data set, our SPH data. Of course, here I should qualify, and I will specify in a moment, that we are not training on every single particle, but we are post-processing the collisions to extract a number of quantities that are, for instance, the masses of the largest remnants, their orbits, the core mass fractions, so that we have parameterized the problem well, so that the surrogate model can learn. And we know of these outcomes to what they correspond in terms of mass of the target, mass of the projectile, impact angle, and impact velocity. So here the known values, the target values are indicated with Y. We have this function that is parametric and is predicting a value HI, and you want the HI for the value of XI is as close as possible to YI. So this process, I'm not gonna go into details into how we train this, but the idea is that you change the value of phi so that you are learning the set of parameters that brings your prediction HI as close as possible to YI. And so this actually is a bit of a picture of what we did schematically for this. We had about 800 SPH simulations that were accumulated through time in the dataset of Professor Asfag of SPH simulations. And as I said, we parameterize the problem, taking the input values in terms of target mass, projectile mass, impact angle, and impact velocity, and associated to them the collision type. So it is merging, it is disruption, hit and run, graze and merge, the remnant mass, their orbits, because of course, if you want to include this in an embodied code, you need to know which orbit the second remnant has in case it is able to escape. So if the projectile is in a hit and run collision, the core mass fraction, and also the debris mass. More technically, the surrogate model were taken as a support vector machine and neural networks, and I can provide more details if you like on this. Of course, part of the data used for training, a part of the data, about 15%, were left out, never shown during the training, and used for testing, which means that you are testing the generalization capability of the surrogate model to predict the right answer or an accurate answer with respect to SPH simulation on unseen data, unseen situations. And the performances were within basically the noise that we can estimate from the SPH simulator. Basically saying that the surrogate model are able to mimic very well the surrogate model is able to mimic very well the SPH simulator. But then now it runs much faster, and so it can be implemented in embodied codes or statistical studies of collisions. Here is just a summary of our current toolbox. We have two classifiers of collision types, which are basically able to say, given the four impact condition, if the collision is merging, the two planets are merging, if it's a graze and merge, a hit and run, disruption. This actually was a fun experience because we basically saw 800 of those videos that I show you at the beginning, the 2D one, and we were saying, okay, this is a hit and run, this is a graze and merge, and then basically we created our own database labeling what basically were the outcomes. And then in a more recent paper, we instead used the criterion based on the existence of a second remnant above a certain mass threshold and the accretion efficiency of the largest remnant to define three different regimes. Then again, the regressor here are are predicting the mass of the largest remnant and the second remnant intended as the projectile of a hit and run collision, so it's able to escape, orbital parameters and core mass fractions. But also we retain the capability in-house to generate more simulations, both with SPH and PKD graph, which is an embody-based collision code. And also we also coupled our tools with planetary differentiation codes, and I will touch on that in a second. Before moving to the applications, I want to make a comparison, for instance, with the scaling laws. Scaling laws, one of the most famous scaling laws for predicting inefficient accretion and hit and run, most used, is from Leonard Stewart and Leonard 2012. Here on the left, in a plane of impact velocity and impact angle, you can see the prediction from our work in terms of the accretion efficiency, which is a parameter that says how much of the mass of the largest remnant changed with respect to the target when the mass of the projectile is taken into account. Basically, how much mass has been deposited or removed from the target because of the collision. And here is the same parameters, but using those scaling laws that I mentioned. So here you can see some similarities between the parameter space. For instance, this curve is similar. This part of the parameter space is similar. But for instance, here the scaling law is using a hard cutoff value for predicting what is a hit and run collision, which is assumed to have accretion efficiency of 0 with what is not. While we are basically finding a more smooth transition and the possibility of having hit and run in a region where hit and run were not predicted to be. And this here you have to imagine that is a 4-dimensional parameter space, and we are slicing the parameter space assuming a value of mass of the target and the mass of the projectile. So that's why it becomes 2D, but in reality it's a 4-dimensional one. We are also, so everything that I show so far is a type of machine learning which is called supervised, which basically means that you know the labels and the predictors, which are the X and Y and X values respectively. However, you can also look for patterns in the data without using the supervised machine learning, using, for instance, clustering analysis, in general, unsupervised machine learning. This is a project led by Rahel Mizari, who is an undergrad student here at U of A, she looking into clustering between the outcomes of collisions. However, to do a clustering analysis and so get a bit of the structure of the parameter space and see if the outcomes cluster as a function, let's say, of angular momentum or impact angle and so forth, you need a large data set of data. We know that there are already some clusters in the parameter space. For instance, if I look at the figure that I showed you before, at least I can see by eye that there are 3 regions like accretion, erosion, and hit and run. So here basically saying you that impact angle and impact velocity are clustering in the parameter space in this way and defining 3 different areas. How we can quantify this? Well, in principle, you can use an SPH simulator, but as we say that this will take forever to generate the parameters, to populate the parameter space so densely that you can do clustering analysis. So what we are trying to do instead is to use the surrogate model, forget that there was an SPH simulator first, and then populate the parameter space using the surrogate model. Because if the surrogate model is well trained, using that or using the SPH simulator is equivalent. Very briefly, Professor Roberto Furfraro from System Engineering Department here at U of A is also using more advanced machine learning techniques, in particular recurrent convolutional generative adversarial networks, that are basically taking the videos that I show you and not only able to discriminate the type of collision directly from those videos without then having that other layer of us like field experts to decide which type of collision is, but also to take that information, define which clumps, so which planets and bodies you can see and find which population of clamps of planets comes out of the collision, and then use that to generate new simulations. This is a very cool project that, of course, is still ongoing at the moment. It's very complex. So now I would like to talk about the applications that we did using this data set, and mostly using the supervised part, so the surrogate models. The first step that we did was to implement the surrogate models in embodied codes, particularly in the Mercury embodied codes by Chambers 2006. This work was led by Dr. Alexander Ensenhuber of University of Bern. And we repeated the embodied simulations of terrestrial planet formation by Chambers 2013, which are simulations in which Chambers used the collision laws by Leonard and Stewart to implement the effect of inefficient accretion and then see if inefficient accretion matters or not. We compare our results using the machine learning model for predicting the collision outcomes to the results instead assuming a perfect merging. So in this sense, perfect merging and efficient accretion using machine learning are two n-members models, because in the former, debris is not produced, and in the latter, debris is produced, but is not tracked if its mass is lower than what the machine learning algorithm has been trained on. And in general, we track the mass of debris, but we don't use the debris, so we don't track the evolution of the debris, and we don't have the debris to have a back reaction basically on the embryos. So this then defines definitely two n-members, because the inefficient accretion model, the debris will be reaccreted in part on the planets. So here on the right is a plot of the mass that is within the embryos as a function of time. So we run 16 simulations, both with perfect merging and efficient accretion. The 16 simulation, each of these simulations has the same initial condition and corresponded to the one with an efficient accretion with the same initial condition. In the black curves are the case of perfect merging, and the red curves are the case of machine learning. So you can see that the mass in the embryos as time goes by is very reduced. This is because the debris is produced and again is not reaccreted. You can also see that the perfect merging scenario kind of ends before, and this is a known result because basically all the small embryos are accreted by the larger planet, while here there is a longer tail of late accretion that goes on. However, again, I want to repeat that these are two n-member scenarios, so the reality will lie somewhere in between, because, like, again, debris are not handled properly in either the two regimes. So if you take those four simulations that I just showed you and you put them on a plane of the locations of the final planets in a heliocentric distance, these are the results for the perfect merging. So every line here is a separate simulation with the same initial condition. The initial mass distributions of the embryos is a single mass initial embryo, so the embryos have all the same mass. And here the colors that you see is representative of the different regions of as a function of heliocentric distance. So for instance, this planet at the end accreted about 1/3 from the inner solar system intended, so inner than 0.75 AU. So here is the results of perfect merging. So the planets are more or less all the same sizes, and they are all large, and there are few planets per system. However, if we hopefully I kind of convinced you during the talk that perfect merging is not to be expected unless in a few cases and in a limited part of the parameter space. And so if you introduce inefficient accretion, you see that the planets that you get are smaller. There is the multiplicity of planets increases. And also there are, for instance, a penury of material in the planets coming from this inner part where the collision velocities are expected to be higher. And they are higher because the orbital velocity is higher. So again, some of these planets could be artifacts because we don't introduce, we don't treat debris as like it should be done. This is something that we are doing as a current and future work. But the idea is that when inefficient accretion is included, you have some planets that survive because of the effect of Hitten runs. And actually, we find that some planets can experience up to 4 collisions, like Hitten runs, and escape accretion. These, of course, are unlucky events, but if you introduce Hitten run collisions and treat them in this way, that's something that can happen. In the improvement with respect to previous work is also that we are treating the deflection angle of the orbit of the second remnant in a more accurate way, which then has an effect, of course, on the orbit in terms of eccentricity, for instance. So the next step onto this was, okay, we see that there are planets that have multiple Hitten run collisions. These planets will progressively lose mantle material, which is the outermost layers, easier to strip. What does it mean in terms of their differentiation, for instance? And also, if you have a Hitten run collision, the core of the projectile doesn't plunge into the target. And so what does it mean in terms of core formation, episodes of core formation through accretion? We team up with Seth Jacobson and Dave Ruby to couple our surrogate models with their silicate metal equilibration model, which is a very cool code that basically uses laboratory constraints and equilibrium chemistry to study, given the difference in pressure and temperature and accretion of material, how the major species and also trace elements in the silicate and in the metal phase, intended as the mantle of the planets and the core of the planets, should evolve through time. And so the main question is if these codes were tested and used for perfect merging cases. So if we introduce the effect of inefficient accretion, what's going to happen? So here is one of the main results of this paper that is currently in revision. Here is, of course, I didn't forget to put points. I'm adding points as we go in the slides. But here is a plot of core mass fraction as a function of mass of the planets. Here, the stars are the solar system terrestrial planets. I would like to precise that these are some planets we know very well the core mass fraction. One example, of course, is Earth. We know of Mercury thanks to Messenger. We have kind of an estimate for Mars. Mars Insight hopefully will provide even more constraints. But for instance, Venus, which will be the star over here, we don't really know, it's kind of an unknown which value of core mass fraction it has. We have estimates from the density, but it could be different. Anyway, here, if you take Mercury and Mars, and these two are Venus and Earth, so the oligarchs, let's say, in the inner solar system, you see that they kind of form this sort of V shape, and I have to shout out to Travis Gabriel and Eric Asfag for noticing this, this kind of interesting thing. So it's kind of pointing toward the direction of the oligarchs. So the vertex of this V shape is on the oligarchs. So the question is, can we reproduce that? And if I add the perfect merging results, the answer is no. And that's not surprising, because the perfect merging, when you sum two planets that have let's say 30% core mass fraction, which is what mostly this is depending on the chemical model that you assume for the early solar system material. But if you basically take two planets and you sum them and it makes a bigger planet, the planet should have more or less a 30% core mass fraction. Here we are about 30, 35. There are some reason why that I can go in more details about this, but the idea is that there is no kind of like spread in core mass fraction, and also there are no small planets, because all the planets they are not able or they don't have giant impacts, and then they remain isolated all the time, or every time that they have a giant impact they are accreted. So there is not small planets that are beaten down or hit and run survivors. If you add the results of the inefficient accretion, we notice two things. The first one is that there is a sort of spread of core mass fraction as a function of mass, meaning that as you go a smaller masses, the diversity of planets increases. But also, if you start counting the number of hit and run collisions that these planets experience, there are planets that, as you go smaller masses, the number of hit and run collisions typically increases, and is contributing to toward higher core mass fractions. The picture is not super clean in this way because it's a stochastic system. For instance, we have also cases in which instead there was a disruptive collision. And this basically, since we are not handling the breeze, probably the planet remained with a high core mass fraction because it got basically removed of its mantle, but then in reality would accrete some of the breeze. And these are, for instance, cases of planets that or outliers, or they were born with a small core nevertheless, because basically they were maybe born away from the sun, and this depends on the particular model of early solar system materials that we assume. However, we are able to reproduce a bulk characteristic of the inner solar system more closely. Of course, these simulations are not meant to be reproducing the inner solar system because they don't include the breeze, and the breeze is not treated correctly and so forth, but is more a proof of concept in this sense. Yeah, this is just a slide to basically summarize with what I just said. So one thing that comes out of this study that we did, the Unsupervised 2020, and this paper I'm leading, is that there is an effect of collision chains. Collision chains are something that basically means that a hit and run survivor can go to impact on another planets or come back to impact on the same planets. So the question is what is gonna happen if you have multiple collisions, and what's the probability that you have multiple collisions? So this triptych of paper, and one paper have been published in 2019, and Senhuber and Aspag 2019, and now we have other two papers in the workings led by Alexander Senhuber and Professor Eric Aspag, that are both in prep, in which we study the effect of collision chains. So in this case, we compare the dynamical fates of simple runners that start as hit and runs on Venus and Earth. So we take Proto-Venus and Proto-Earth at 0.7 AU and 1 AU respectively. And we follow the evolution of these hit and run survivors while they basically evolve under the influence of the major planets to impact then on other planets or never impact again. And the first collision is treated with SPH. Then the evolution of the different possible evolution from that collision of the runner exiting at different angles from this collision are treated using using the surrogate model for the reason that this makes the study statistically possible. And here is a kind of a complex plot, but I think it's very cool. So here is the case of a slow runner, for instance, which is the case of a velocity of 1.15 times the escape velocity. So this projectile is coming at that velocity and an angle of 45.5 degrees. And here is a faster projectile that comes at also a higher impact angle. So here is like if you impact in Venus, you have that for those planets, for those hit and all of them are hit and runs. So if you evolve them, the majority will impact again on Venus. Some of them will go to impact on Earth, and some of them will never impact with none of these planets again. And then you get like what survives of those that are hit and run, and then you keep evolving them. So you study like these what are defined collision chains. And the same also for Earth. So the main finding that we have on this is that runners that emerge from Earth, so basically this part here, have the same probability to impact Earth and Venus. So they could impact equally probable the both planets in their follow-up collision. However, it's unlikely for a runner coming out on Venus to impact on Earth. And the collision chains more likely end at Venus and Earth. So Venus kind of hold to its runners in a certain sense. And there is a general trend for runners to move toward the center of the solar system. Runner are again the surviving projectiles in a hit and run collision. And here I just want to point out that an interesting thing that we see is that as you go on more and more collision chain, surviving of collisions, which becomes of course less and less likely, you have that the probability of surviving also increases, which is something that is very interesting, probably related to the velocity of the collisions. Briefly, I would like also to touch on this paper led by Eric Aspag, in which we are looking at a case of collision chains for a case of moon formation. Indeed, we have evidence through papers in literature and also our own work that hit and run collisions should be as common as accretion. So if you have like giant impacts on Earth, about half of them should have been hit and run collisions. So what this means in terms of geochemical and geophysical consequences for the planet. Here again is a map of accretion efficiency using the surrogate models for the case, the canonical case of proto-Earth and prototheia impacting. And you can see that there is a large diversity of giant impact outcomes. The majority of the parameter space is taken by the hit and run scenario. However, I should also precise that not all velocity and angles are equiprobable. Actually, there is a distribution that picks up 45 degrees for the angles, and the velocity, let's say the bulk of the velocity are below 2 times the escape velocity. Briefly, the idea then is a 3-act like a scenario. We have an initial collision. The collision is a hit and run. So it's not a merger, it creates some mixing, but doesn't basically create that disk that is basically needed in which the core of prototheia or theia goes inside Earth and leaving this disk from which then the moon accretes. And the idea then is that this projectile at a certain point comes back because it remains in a similar orbit, and then it comes back in a condition in which indeed there is what is the canonical scenario, in which you create this disk and the moon accretes out of this disk. One added advantage of this proposed scenario is that not only you get like a disk that is compatible with the canonical model and also the angular momentum, it's okay, but also you get an inclined disk. On future work, we are building a new data set of SPH simulation. This is actually, I think is really cool because the SPH simulation that I used in my thesis to train these the surrogates model were not meant to do that, to be used to do that. So it was a data set that was sparse and partially incomplete in some part that of the parameter space. However, the networks were, like in the surrogates model, trained well nevertheless. But we can do better if we have like a data set of SPH simulation fully designed for this particular application. We took an idea from Tim et al. 2020 that did a similar work of using a Latin hypercube sampling of the parameter space, which is a way of sampling that in multi-dimension that it's an optimal way to do it. We are also adding a new variable, which is a variable initial core mass fraction. I should have precised that all our collisions in the data set that I spoke about were all 30% core mass fraction. But of course, you can have different core mass fractions, and also during the collision chains, we use an approximated criterion to treat the core mass fraction. However, having like that every core mass fraction can be used as an input would be, of course, an added level of accuracy. And we are also expanding the mass range. Now, before like this kind of a training box was where we are expanding toward the larger masses, so toward what would be like super Earths, rocky super Earths, but we are not treating the atmospheric envelope. This is because the question of state becomes like important at those levels, so we are only considering the rocky part. And then you can go at smaller scales toward basically what are major collisions between asteroids, so to try to answer, for instance, question about how asteroids like 16 Psyche formed. We are also going even lower than that toward the small kingdom, using then other softwares like PKD-Graph, which is this embodied code based collision embody based collision code. And the question then becomes like when strength and friction start to matter and become like, and the dominance of gravity, that is what dominates the collision between large bodies, start to lessen. For now, this part is led by Dr. Steven Schwartz here at U of A. And basically these collisions, we are piling up databases from collaborator, Martin Yuzzi from the University of Bern, Keisuke Sugura from the University of Tokyo, and also creating our own. So in this, basically we'll create a kind of sort of continuous spectrum of masses that we can then use, and this is like my last slide, to kind of like change a bit the idea of how we approach, interpret the putative collision outcomes. For instance, I don't know, the formation of Mercury. And the idea there is that before, like, we just run simulations and see how this simulation, like what's the outcome, and see, okay, this simulation produces like an outcome that is similar to what, like, I don't know, the core mass fraction of Mercury and the mass of Mercury, or the mass of the moon. But however, using surrogate models, because they are very fast and accurate, we could technically do an inversion, statistical inversion of outcomes. So finding those impact conditions that are the most statistically probable. We did some preliminary work on this. We presented EPSC now 2 years ago, on Mercury. Here you see our probability distribution of basically the collision parameters, the collision condition, if you invert for mass and core mass fraction. But the idea then is to use the geochemical models, as I showed, to include other constraints. And this has also interesting application, for instance, for the formation of Psyche, and also for interpreting observation like super Earths with Mercury-like compositions like K2-9b. So this was my last slide, and I would like to acknowledge that this research has been carried out on the traditional lands of the Tohono O'odham people, where also this presentation will be broadcasted. And we acknowledge support from this NASA grant that really made this work possible. And the main points I would like to communicate is that inefficient accretion is important. It must be realistically modeled. One of the ways in which we can do it is using machine learning. There are some intrinsic advantages. You can protect against overfitting the data, and you are not choosing an ad hoc function. You're not making physical assumptions, but it's full data driven. And the surrogate model can indeed be used to improve realism, but the idea of surrogate model is not limited to like the case of planet formation. It's kind of a general concept that I'm generally using in my research, and actually we submitted a book chapter for a forthcoming book about this idea of surrogate model that hopefully will come out soon. I would like to thank you for the attention, and I think I went a bit longer than I thought, but I would like to take any question you may have.
All right, thank you so much, Saverio. I'd like to invite everyone to unmute and applaud this very interesting talk.
Thank you very much.
All right, if you have questions, you can either use the raise hand feature, which in the updated version of Zoom is under the reactions tab, or you can put your questions in the chat if you would like the organizers to ask them for you. And then if you are not in the updated version of Zoom, the raise hand feature is still going to be under the participants tab.
I'm afraid I put everybody asleep.
So just out of curiosity, while we're waiting for people to formulate questions, what kind of computers are you using to run your machine learning? Are you doing it on like a desktop or a cluster? And how long does it take you to like get through a set of models?
So for these particular applications, we didn't use deep networks, but we used shallow networks because we found that we're able to achieve like the level of noise, level of accuracy that we wanted. So these have been able to run it on a desktop. However, like for some, for instance, for other application, if you needed to generate like the simulations, we used the high computing cluster, high performance computing cluster, U of A, like extensively. Particularly Dr. Enzo Huber did that to generate the new SPH simulations and all the embody codes. So it becomes a more like for now, like the computationally expensive part was generating the data set, but not training the neural networks.
All right. Any additional questions? Oh, Phil.
Yeah, hi, Saverio. Those are a really nice talk. I was wondering, have you compared the results of the surrogate model to SPH simulations from other groups, other SPH codes, maybe other equations of state?
Yeah, that's a great question. We didn't do it yet, and it's something that we should. The problem is, as you pointed out, there could be different equation of states, and there could be different, like, say, hidden parameters because we are not training on them. So the outcome could be different. There is some for the major like properties like mass and core mass fraction, yeah, different algorithms have been proved in papers to provide similar results. However, this actually it's a very important point, and we would need to expand on it. Yeah, there are papers like, for instance, Tim et al. 2020 that does a similar work to what we do with a different data set. So encourage you to check it out if you are interested in these, but we didn't cross-checked for now the analysis. Thank you for your question.
All right, and then we have a couple of questions from Stan Yen in the chat, who asks, can you put constraints on the initial conditions from data inversion, and how much uncertainty is in the obtained initial conditions?
Yeah, that's a great question. So definitely you can put constraints, like it depends on the particular case. This is still an ongoing process, but in principle, you could invert, like if you have data and a model to invert. There are two problems. So the first one is how to handle a priori information. So we have like priori information, for instance, from the dynamical simulations, so which are the most likely conditions, but then introducing them could create problems, because then you have that if you choose basically the wrong a priori, you can polarize like the solution toward, bias the solution toward wrong results. And how much uncertainty is in obtaining initial conditions? That's a great question. They could be very large. It depends again on the cases, because if you have like you have end up that there is not that you cannot constrain, or if you have the generate solution, then one idea is, for instance, to introduce another like information. One example could be other information from NASA Messenger by NASA Messenger for Mercury, or for coming data from Bepi Colombo. But yeah, that's a great question, and it's something that really depends on case by case. But it could be that like then the problem becomes unconstrained and so forth.
All right, Eugene.
Hi, Saverio. That was a nice talk. And thanks for addressing my earlier question. I have another one, which is, could you give us a sense of how much debris is created? So what fraction of the mass? I mean, presumably below a certain size, you sort of stop tracking it, right? It's just exploded out from the event. And I know it depends, of course, on the scenario, but if you could give us just a rough sense of how much mass is quote unquote lost from the system, or is converted into debris that you no longer track.
Yeah, absolutely. I can actually go back to this. Thank you for your question. So we track in terms of mass, we track the debris quite well, because like if you get like the two major planets and then you get the two remnants or one remnant, everything that is left is like the mass of the debris. However, you can see here that like there is a substantial mass loss, and we get like 1.5 Earth masses of debris. So that's of course like a low end member. As I said, like the realism is definitely in between these perfect merging and efficient accretion as we handle it for now, and this is an embodied code decision, and also because we are not tracking the evolution of the debris. However, we should, and we have to introduce that for not only for a mass problem in the sense that the larger planets are more likely to sweep the debris, but because also the debris can basically dampen the eccentricity and inclination, and has an effect on the orbits of the planets. So this is definitely a point that we need to take into account. But the idea is that, like, for instance, the diversity that we have at smaller scales, both because like debris that are created from larger collisions may become like even more erosive when they collide on smaller bodies, and also because the larger body are expected to accrete part of the debris, then these like would maybe lead even to an enhanced diversity at small scales. But definitely it's an open question because we are working on it because we have to introduce it in an embodied code. So
it just looks like sorry, I'm having a little bit difficulty reading the plot. Sure. So am I to read from this plot that the conversion efficiency into debris is something order unity, like 50% of the mass? There is
a catastrophic mass loss from the embryos. if you introduce the effect of inefficient accretion without handling that debris. That's the as you correctly noticed, this is is not the case in the sense that you will have debris reaccreted and interacting with the planet. But yeah, if you don't handle debris smaller than the second remnant in hit and run collision, you lose a lot of masses in the system, and the planets that you end up are very small.
Okay, thanks.
Thank you for your question.
All right, it is past the hour, so we're going to end it there. Thank you everyone so much for coming, and thank you once again, Saverio, for an excellent talk. See you all.
Thank you very much.
Thank you.
Thank you. If you have any
Thank
questions,
you, Saverio.
this is my address if you have any question. Thank you very much. Bye. Thank you.